So the first part of the roadmap, the relationship, first of all, between moles and particles, and then the first way to measure, in quotes, the number of moles to weigh out a pure substance is extremely important. But probably the most important aspect of the roadmap is the way in which once you know moles of one substance, you can convert it to moles of another related substance. And in most cases, that relationship comes from a chemical reaction, which we describe with a chemical equation, and it's not an equation unless things are equal. And of course, the things that are equal are the number of atoms with which you start must be the same as the number of atoms of each type with which you end. And in order to describe the chemical reaction appropriately, we need to learn how to balance those equations. Now, we did a lot of simplistic balancing in the movies, and then associated with the movies, those quizzes. So in the worksheet, I want to make these a little bit more demanding. So start with one that is actually relatively straightforward in terms of a lot of things, but you do have to keep your wits about you. We have this nice big organic molecule, C8H18O3, which we are reacting with oxygen. We're combusting it to make hydrogen oxide and carbon dioxide, otherwise water and carbon dioxide. So to balance it, we say, how many atoms do we start with? Well, the way I've described it so far, I've got 8 carbons, 5 oxygens, and 18 hydrogens. So notice it's 5 oxygens because we not only have O2, but we have 3 in the combusting molecule with which we're starting. So I hope by now you're at the point where we say, well, when we're combusting something that's got carbons and hydrogens, all the carbons go to CO2, all the hydrogens go to H2O, which means that we're going to have 8 carbons on this side, so 8 CO2s, 18 hydrogens, so 9 H2Os. So let's pop those straight in, shall we? And now let's recalculate the number of atoms. So now we've got 8 carbons, as we suspected, with the CO2s, no doubt there. There's our 18 hydrogens, nicely balanced. And of course, we've gone way over the number of oxygens. We've got 9 there, plus 16 there for 25. So how do we adjust what's on the left-hand side to make 25 oxygens to match up with the right-hand side? Well, the first thing we do is we remember we got 3 oxygens here, so thus we only need another 22 oxygens to get up to 25, and 22 oxygens can quite easily come from 11 O2s. So pop that 11 in there, and now everything's nice and balanced, and we feel very happy and know that we can balance equations. So let's make it a little bit more interesting, shall we? Ca3PO4 twice goes to SiO2 plus carbon, goes to CaSiO3 plus CO plus P4. Looking at the number of atoms overall, we see we got 3 calciums here, 1 calcium there, 2 phosphoruses there, 4 phosphoruses here, 10 oxygens, 4 oxygens, and then of course a variety of silicons and carbons. Now several things that one can start off with here. We could multiply the number of calcium silicates by 3 to get the calciums matched up, but I would prefer to say, well, I've got 4 phosphoruses here that determines the number of phosphoruses over here, so why don't I make the phosphoruses equal? And to do that, I need to put a 2 in front of this Ca3PO4 twice. So let's recalculate now. Now our phosphoruses are good. We haven't touched silicons and oxygens, silicons and carbons. Oxygens, of course, usually the last atom or one of the last atoms to balance because it usually occurs in so many things. So now let's go ahead and address the calciums. 6 calciums here, so we need 6 here, which means we need to put 6 in front of the CaSiO3. Recalculating everything there. Calciums are good, phosphoruses are good, oxygens a lot closer than they were, silicons out of whack, carbon's still good. So let's go ahead now and do the silicons because it's pretty easy to see what to do with the silicons. We got 6 on the right, we need 6 on the left, we need to therefore put a 6 in front of the SiO2. Recalculate, oxygens going totally crazy. Silicons now matched up, calcium's phosphorus matched up, Carbons are still looking good. Now, the next thing we need to do is change the oxygens. We need to get more oxygens on the right-hand side. Oxygen occurs in two places. It occurs here. Well, we don't really want to mess with this, because if we mess with this, we'll mess with calciums and silicons. And it occurs here in CO. So why don't we just say, well, we need another 9 oxygens on the right-hand side. So let's have another 9 COs, which gives us now a total of 10 COs. Match all that up, and now everything's nice except the carbons for the first time have got out of whack. But that's okay, because to adjust the carbons on the left-hand side, we just need to adjust the number of carbons on the left-hand side. So we want a total of 10. So we'll take 10 there. So the coefficient of carbon, which is what was requested, is 10. Kind of a fun one. Some of you might be looking at thinking, isn't there a way we could do it using redox equations? And the answer to that is absolutely. But if you want to try doing it with redox equations, I think you'll find that even with that, this inspection method worked better. Another nasty, disgusting one. Again, those of you who know how to balance redox will see that there's a way to do this, but we don't know that yet, so we're just going to go ahead and balance by inspection. SHN and O atoms, left-hand side, 1 of each until the oxygens with 3. Right-hand side, a little bit nastier, 1 sulfur and nitrogen, 7 oxygens and 4 hydrogens. So which should we start with? Well, I can see readily how to turn 1 hydrogen into 4. I can't see readily how to turn 3 oxygens into 7. So let's go ahead and just make this 1 hydrogen 4 by putting a 4 in front of the HNO3. Recalculate, and we see now our nitrogens are out of whack. So we'll go ahead and on the right-hand side, turn this 1 nitrogen into 4 by putting a 4 in front of the NO2. Recalculate there, and we have 1, 4, 4 ecstatic, but now 13 here and 12 oxygens on the left-hand side. So we need another oxygen on the left-hand side. The only thing we can adjust with the oxygens is HNO3. Now I could try putting 5 HNO3s, except I should see that on the right-hand side, hydrogens come in chunks of 2. So therefore, if I'm going to have an odd number of hydrogens here, that wouldn't match up here. So let's stay with an even number of hydrogens on the left-hand side. 4 doesn't work, so let's try the next one using 6. So now 6 HNO3s, recalculate. Again, sulfur fine, got too many hydrogens. We've again messed with the nitrogen here. Nitrogen's the easier one to see what to do, because nitrogen only occurs once on the right-hand side. We need to turn this 4 into 6. And now calculate. Sulfur's good, nitrogen's good. Hydrogen's messed up, oxygen's messed up, but now hydrogen's here, and thinking about it, we need 2 more hydrogens on the right-hand side. We need 1 more oxygen on the right-hand side. 2 hydrogens, 1 oxygen. We just need another water. Recalculate there, and we've got 1, 6, 6, 18. What's the coefficient of the water? Rather mundanely, 2 after all that messing around. Now, as a final one to balance, although of course we'll be balancing equations throughout the rest of the worksheet, what's the sum of the 4 coefficients here in this rather nasty looking one again? Again, it's a redox equation for those who like to do redox equations. But anyway, let's see what we got. We've got 1, 2, 2 nitrogen, oxygen, hydrogens on the left-hand side, 1, 1, 5 over here. Now in this case, we could go ahead and we could balance it in a couple of ways. We could look at the oxygens and say, well, we need 2 here. Well, that would give us 5 hydrogens, or 7 hydrogens there, and 2 here. Or we can go ahead and we can actually look at the hydrogens and say, well, I need 2 to turn 2 and 5 into the same thing. Well, if it was a nice easy one, I would just multiply the 2 by 5, and I would just multiply the 5 by 2. So let's do that. Let's have 5 H2s and 2 NH3s and 2 H2Os. So what we've done there is we've multiplied by the 2 by 5 and 5 by 2. Recalculate everything, and now the only thing we've actually got to address now is the nitrogens. We need 1 more nitrogen on the left-hand side, so I'll put a 2 in front of that. But of course, we recalculate. 2, 4, 10. So the only thing extra we need is another couple of oxygens on the right hand side. So we'll turn that 2 H2Os into 4. Now 2, 4, 14. So you'd say, well, hang on, we've messed up the hydrogens. That's okay. It's easy to get more hydrogens on the left hand side. We just have to turn that 5 into 7 to give us 14 in total. So a rather sneaky one there, and an even more sneaky one at the end of it is I don't say what's the coefficient of something, I say what's the sum of all the coefficients, well it's 2 plus 7 plus 2 plus 4, which is 15. Several ways that you could have addressed this particular one. That was just one way to illustrate an extra sneaky cognitive way to think about it.